Welcome to the Cosmic Pie Podcast, Season 2, Episode 11. I'm your host, Wayne Barkhouse, and here with me is...
Robert Moore.
So we are broadcasting live here on the campus of the University of North Dakota here in Grand Forks, North Dakota. We do have a live chat that's running, so at any time you feel like you'd like to send us a comment or have a question or anything like that, please use the live chat, and we will stop what we're talking about and address it immediately.
Yep. Well, maybe not immediately, but we'll get there.
Within 60
Promise
seconds,
you.
right?
Yeah.
How's that?
Something like that.
Now, as a disclaimer, whatever Robert and I say today is totally the personal opinions of Robert and I, and not necessarily the opinions of anyone else in the world, any organization, any university, any college, anybody anywhere.
As long as it is a statement of opinion, anyway.
Now, that doesn't mean, of course, Robert, that there's no one out there in this world that agrees with us. There may be.
Right.
And they don't have to agree with everything. Maybe they agree, which is part of what we say.
Yep. But here we already got a question. You know that?
What's the question, Robert?
The question from Mizuho Schwalm is, did the geomagnetic storm arrive?
Yeah, so
there was a geomagnetic storm, and I think it has arrived.
Yeah, and the last thing I heard, it didn't cause a big aurora display, as we would think. And that's a good question because people naturally think, if you're a layperson and you kind of keep track a little bit about the activity of the northern lights and so on, southern lights, of course, if you're in Australia, that anytime we have a solar storm or an eruption on the sun, and those particles are usually charged particles, when they interact with our magnetic field here on Earth and they spiral around magnetic field lines, crash into the polar and the polar regions of the upper atmosphere, that they essentially cause electrons to be boosted to higher energy levels, and they descend downwards and give off light.
Makes them glow.
And they glow, and that's the aurora display. And you'd think that anytime there's some type of event like that on the...
Muted, okay. Interesting.
Are we muted?
No, we're not.
Okay.
I'll move your slider up a little bit.
Sound keeps muting. We may be having technical problems.
It may be technical problems because, we're not changing anything here. So
yeah, we should just continue on.
Yeah, I'm going to have to muddle through.
Anyway, so anytime that there's an eruption or some kind of a storm-like event that's happening on the sun... It's on mine. Okay, so we're okay. Good, thank you.
Thank you.
So anytime there's an event on the sun, we naturally assume that's going to cause an effect related to the aurora, and that's not always the case. And we don't have a good understanding why that's not the case, that we'd always have a storm, we always have an aurora. And this is one of those events, as far as I understand, is we thought we'd have this great display, and yet we don't seem to be seeing it, at least the last time I checked.
Yeah, I haven't seen anything yet.
Yeah, so there's something that we're missing, right? There's a lot of nitty-gritty detail involved in the interaction of charged particles with the magnetic field and the atmosphere and all of those things. So,
and for those that don't know, we do have somebody doing research on the northern lights here at this university, so we kind of hear when there's going to be a good display.
In fact, we have dedicated cameras, a network to monitor the Aurora Borealis. In fact, if you search for UND Aurora Cam, NODAC is the project name, and you will see that. I'm actually part of that project, just as a disclaimer here. So we do have that's running, and that's running all the time, so you'll be able to look at the night sky, and anytime that's clear, of course, from about an hour's drive north of where we are here in Grand Forks. So you could please check that out when you have time. In fact, we'll try to get, we had Vincent Lavida talk about Northern Lights here a few podcasts back, and we'll either get Vincent on again or get somebody else to talk about it if they're willing.
Absolutely. Vincent was a good guest.
Yeah, definitely. So today I thought we'd start, Robert, by updating everybody on some news that we've talked about in the last couple months. So if you want to go to our first slide. And this involves the Odysseus spacecraft that landed on the moon. This is the one that was launched by Intuitive Machines. So it's the one when it landed, it was going sideways at the same time it was touching down, and so it flipped over a little bit, roughly 30 degrees or so from vertical.
Right.
And it was designed it has solar panels, so it was designed to be able to function as long as the sun was above the horizon.
Right.
And once the moon itself, that part of the moon, which is near the South Pole where the spacecraft landed, in fact, it's the closest surviving spacecraft to the actual South Pole of the moon itself.
Yep.
It was within 10 degrees, if I remember correctly, in
latitude
of the South Pole on the moon. that when nighttime came, so no longer are you receiving energy from using the solar panels, of course, then the battery just kind of went dead, and that would be the end of the spacecraft. So they actually shut it down and just left minimum sort of electronics running, probably so the thing wouldn't freeze up solid and still
heater,
function. Yeah. And the hope was after 2 weeks, which is the typical length of a nighttime and a daytime when you're on the moon, because it takes roughly a month to go around the Earth once. So one part of the moon has approximately 2 weeks of daylight and then 2 weeks of nighttime, where the sun is below the horizon. That when it came to the point where the sun was now high enough above the horizon where the solar panel should be illuminated enough that it would generate plenty of electricity to run the instruments, the spacecraft itself just didn't respond to any commands. So it has been officially declared as dead. So the Odysseus mission is over. So rest in peace, Odysseus.
Indeed. It was a good shot, and it did some work before it finally pooped out.
Well, don't forget there are going to be, the next one, Odysseus 1, 2, 3, there's going to be multiple spacecraft that intuitive machines have planned, are on the books here to go back to the moon to prove the technology and just make it better and better and better, right? To perfect that technology and then hopefully make it extremely cheap. That's one of the goals, I'm sure. Really cheap to send up, small type of experiments. So when these micro satellites instead of these micro experiments on board the spacecraft itself. And there were a couple of them this time. There was one package that had to deal with, I think it was like a ball with cameras on it, and the lander would eject this ball on the surface, and then the cameras would look back on, at different places along the surface to see different, part of the landscape of the moon, and also there'd be a camera hopefully pointed towards the lander itself to be able to get an image of what kind of condition it was in. And that never worked as far as I know.
I don't think it did.
And that was developed by the group there at Embry-Riddle in Daytona Beach in Florida.
Okay.
So, but that's the idea, right? You can have these different colleges and universities or groups, if you can raise enough money, to put these little experimental packages then on the surface of the moon.
Right.
And that can go a long ways in advancing science, especially, nowadays where there's the big push, of course, for the United States, not just the United States, but other countries have their mind focused on the moon more so than what it was back in the 70s or 80s, for example.
Right.
And
70s or 80s, there were really only 2 nations that could remotely do anything like that. So,
yeah.
It's just one of those things. We did it, but Germany was still recovering from Second World War. England was as well. It was open landscape. It was not an open landscape.
Well, once the United States landed on the moon in the late 60s, with people in 69, that took the oomph out of the desire of the Soviet Union to try to get there because the record was taken at that point.
Right.
So I know they landed some landers on the moon and brought back soil samples and stuff, and then had rovers on the moon as well. But that's about it. Then they turned their focus to putting up space stations in orbit around the Earth, and that has been their focus since.
Right.
And there were the Salyut and the Mir, and then part of the International Space Station, and then I guess their plans is to put up their own space station with China in the future, and after the International Space Station. Yeah, that
doesn't surprise me.
That's their goal right now. Who knows in the future, right? A lot of things can. And don't forget the space program. It takes a lot of money.
It does.
Right? It's not easy and cheap, right? So it's hard, it's difficult, it's very technical, and it costs a lot of dollars. So if your country can afford it, I guess you can think about these things. But if you get in a situation where maybe there's an economic downturn, or you don't have quite the money, and the people don't want you to spend it on certain things, then that can have a lasting impact on what you actually do in terms of space exploration.
And I will say, for the no more than we spend on it, we're doing quite well, because it's not a top priority even now here in the States. Not like it was back in the Apollo days anyway.
Yeah, we're actually going to pick up this discussion related to money and budgets a little bit later on in this podcast. But right now, we're going to turn our attention to something that doesn't cost anything.
It doesn't cost
anything. It's a freebie, Robert.
Right.
A freebie. How often do you hear that?
Not very often.
So let's go to the next slide, if you would, please. We're going to talk about this very interesting event that is scheduled to take place because it happens every roughly 80 years, and that 80 years is essentially up now. So this is the eruption, essentially, of a star system, a binary star system that is 2 stars in orbit around each other, known as T. Coronae Borealis. So it's in the constellation of Borealis, which is actually, the constellation itself is diagrammed out on the right-hand side. It's near the constellation Hercules. That's usually an easy one to find in the sky.
Because that little, you can't see my finger pointing, but if you look in the upper left, there's that little keystone-shaped group of stars that is easy to spot, and that's Hercules.
Yeah. And the one that we're focused on to the right of Hercules in this diagram, it's called the Northern Crown.
Northern Crown.
And so it looks like a crown. It's like half of a circle, and you can see, hopefully, right near the circle part that I'm talking about, there's a red circle. And that encloses the location of this star system, T Coronae Borealis. Now, what's so special about this system? Well, way back in 1217. So, Robert, what were you doing back in 1217?
1217, starving mainly. It was real hard to get any hold of any bread back then. We had a few bad harvests that year.
So back in 1217, I believe a priest, a Catholic priest at an abbey, does that
Wouldn't
make sense?
surprise me.
Right, had noticed the brightening of this area of the sky where that red circle is denoted on that right side on that panel there, and had reported it. And this information, of course, was put in some records, and those records survived so that we can look at it in more modern times. And what he was actually seeing was something that we call a nova.
Mm-hmm.
Now,
Not a supernova.
Right, a nova. Now, nova is what, Latin, I guess, for new?
New star.
Yeah, it just means new, right? Nova
think so, yeah.
means new. So the nova was designated here as the appearance of, suddenly, of a new star that wasn't there before, and bright enough that you could see with the unaided eye. Back in 1217, there weren't any telescopes that one could use. And so that didn't come along until the very late 1500s, and then Galileo comes along in the early 1600s and uses the telescope to make his observation, and eventually publishes a book on what he saw. But back in 1217, there are no telescopes, so whatever you see in the sky, you see with your eyes. And so it was observed the appearance of a new star in the sky. Now, it turns out, of course, we can study this object today, and what nova are, as far as we know, that they are two stars. One star is what we call a white dwarf.
A white dwarf.
Now, a white dwarf is the end state of a low-mass star. So a star, when an object first becomes a star, and this occurs to all newly formed stars, they are converting hydrogen to helium in their cores.
Which releases energy, which is what gets them nice and hot, produces pressure, counters gravity, and they get stable for a while.
Right, and so in astrophysics, we say that those stars are on the main sequence of the Hertzsprung-Russell diagram, which is a diagram of luminosity versus surface temperature, mainly. Mm-hmm. Okay. Now, the sun, for example, our own star, if you like, it's also one of these main sequence stars, happily converting hydrogen to helium in its core. Eventually, for stars that have a mass about 8 times the mass of our sun and smaller than that value, they end up, after going through their various life cycles, the first one being, of course, the main sequence phase, they end up turning into something that we call a white dwarf. Now, perspective on size, our sun is about 109 times the size of the Earth.
Right.
When our sun ultimately forms a white dwarf, it is about the size of the Earth.
It's essentially just the core of a star.
Right, so you're going to go down to about 1/100th the present size of the sun when our sun turns into a white dwarf.
But it should be noted it'll still have about half the mass of the sun. But
well, at this we can get into this, at some point. But the other thing is that the star has collapsed to the point where, at least classically, so we're not going to think about quantum mechanics. You can think of jamming marbles in a glass vase or something.
Right.
And you could calculate how many marbles can I put in this glass vase. Well, you could calculate knowing the volume of the vase and the volume of the marbles, knowing that there's going to be space between the marbles, of course. Mm-hmm. So you could do it by I can calculate it, and then I'm going to compare that calculation actually doing the experiment. So right. You put marbles in a glass vase, and let's say, I think I can put one more marble in here. And you try to put it in, you put the marble on top of the pile, on top of the opening of the glass vase, and it just falls over the side. It's like trying to fill up a glass full of water, and you keep adding water. It's not going to increase the amount of water in that glass. It's just going to go over the side, right? The extra water. And so you could push on it with the palm of your hand, trying to jam that last marble into the glass vase. But ultimately what you'll end up doing is probably cracking or breaking the glass container itself if you push on it with enough force. So there's a limit to how many marbles you can get into a glass container like that. And you could think of it, and this is like classically, so it's not really the true way, but I'm just trying to do by analogy to keep things very simple for those of you that are listening that haven't taken physics or forget all about physics in the past. That you can think of electrons as these marbles jammed side by side, and they resist getting any closer together. And in physics, we call that electron degeneracy pressure.
Right.
And that's essentially what prevents a white dwarf from continuing to collapse, within itself due to gravity. It stops the collapse.
The electrons don't want to be any closer to each other than a certain limit.
So in quantum mechanics, we can think of it as the Pauli exclusion principle, for example, is a way of thinking about it. But anyway, so these white dwarfs then are stable from collapse because of this electron pressure, and they would sort of stay like that essentially forever. So our sun, for example, when it turns into a white dwarf, all it will do once it gets to that phase is essentially cool off and get colder and colder and colder until eventually it reaches the background temperature of outer space, which today is about 3 Kelvin.
Right.
Now, what's 3 Kelvin? Well, it's about minus 270 degrees centigrade or Celsius. So if you think it's cold outside today, Robert, imagine if the temperature was 3 Kelvin outside.
I was about to say, so last winter here in North Dakota?
I wonder if my car would start at 3 Kelvin outside.
Probably not. I'm going to go out on a limb and say, it'd just kind of be a frozen block.
Well, even if you manage to roll it over, you can imagine the grinding of the gears inside the pistons and the cylinder walls.
Because of the contraction of the metal.
The oil would be solid. Right?
Oil would be solid. So all these nice things would be happening. So
now, the interesting thing happens, though, if you end up having a white dwarf that's not totally isolated. That happens to be where we think the majority of stars are in systems that contain 2 or more stars. So we could have a case where you have 2 stars in orbit around each other. They orbit their center of mass. We call that a binary star system. And if one of those stars was a low mass star when it was a main sequence star, let's say an 8 solar mass star, and that turned into a white dwarf, and the other star, let's say, had even less mass when it was on the main sequence. So it turns out that the time that it takes for a star to go through all phases of its life is dependent on its mass. So the life expectancy of a star is mass dependent. The higher the mass, the shorter the period of time that's required to go through all of its evolution, ultimately die.
I like likening it to a big SUV with a 30-gallon gas tank and a little, Q car or whatever it is, the little bitty tiny little things, having only like an 8-gallon tank. Well, that little car could still go further than the SUV, even though it's got a third the size of the tank. Sure, it has less, the smaller mass star has less mass, less fuel, but it can burn it at a lower rate.
Can I mention the disclaimer once again before I say the next comment?
I know. It's a very simple analogy.
No. I mean, my comment that's coming now is going to be politically incorrect.
Oh, okay.
So if you don't like to hear this stuff, close your ears right about now. Imagine that you're a person that weighs 1,000 pounds, right? You're going to live a lot shorter life than somebody who weighs like 150 pounds.
Right.
And statistically, right?
Statistically, yeah.
So you can think of it that way, right? That the more mass you have, the chances are you're going to live a shorter period of life, compared to someone whose BMI is in the right range. Put it that way.
Yeah, we won't talk about that.
Moving on. So when you have a system like this, where you have binary star system, where you have, let's say, one star that has evolved to the point where it's become a white dwarf, and the other star had less mass, so it takes longer for it to go through its life cycle. In fact, the one star could be a white dwarf, and the other star is still on the main sequence. But ultimately, what can happen, of course, is that star that's on the main sequence, it'll evolve off the main sequence when it's happily finished converting hydrogen to helium in its core. And what happens then is the core of helium begins to get smaller and heat up, and eventually the hydrogen immediately surrounding that core reaches 10 million Kelvin, allows sustained hydrogen fusion to occur. And that shell burning, as we say, gets thicker and thicker as the helium core continues to get smaller and heat up and get hotter and hotter and hotter. And that shell burning process ultimately causes the whole star to expand.
Right.
So on the outside, if you were observing from a safe distance, you would see the star over time getting larger and larger and larger, and also redder and redder. Why? Because the outermost atmosphere is getting further and further from the energy source, from the furnace in the center of the star.
So it's getting cooler.
So it's getting cooler, and what happens to the color?
It goes to red.
Yeah, it gets longer wavelength, the peak emission, right? So these things are known as
Red giants.
red giants. So what we think is happening in this star system in particular is that this star that is turned into a red giant is swelling up. And if it gets large enough, some of that outer material, that outer gas, can actually feel a stronger gravitational pull towards the nearby white dwarf than to itself. So its self-gravity, if you like, is less than the force of attraction towards the white dwarf. So in other words, the white dwarf can peel off some of that material in the outer atmosphere of the red giant. Now, this system is moving and rotating, so the material doesn't fall straight in. It goes into an accretion disk, the spiral-like pattern, because of the conservation of angular momentum.
Yep.
And so ultimately, the material will crash on the surface of the white dwarf. And as far as we know, what happens is that will build up, and then ultimately will ignite. And so you get this flaring. It's like pouring gas on a bonfire. You get this flaring of the gas. That excess gas that you just put on the fire then will burn away, and then the fire will return back to its normal sort of brightness that it had prior to pouring the gas on it.
Now, I do have a question, because this is essentially the same process that happens with a type of supernova called a Type 1A. So what makes this one go nova, where it just ignites hydrogen fusion in the gas that's fallen onto it, instead of it crushing down to a neutron star and exploding?
Good question, Robert. Well, it turns out that if you do the experiment, you have a white dwarf, and let's say, okay, it's not going to collapse because of electron pressure.
Right.
But will that be the case if I keep adding little parcels, little bits of matter to the white dwarf? I keep adding material, I build up its mass, Eventually, when the mass of that white dwarf reaches about 1.4 times the mass of our sun, even electron pressure cannot support that star from collapsing in on itself. It collapses in on itself, and that's when we have the supernova type 1A. So the whole thing blows up as one of these carbon detonation supernova.
Right.
So this white dwarf is not at that limit. If it were, and it acquired enough material to push it over that mass limit, which by the way is called the Chandrasekhar mass limit, then it would go Type 1A supernova.
So it's that this white dwarf has started out at a position where it can't build up enough.
Yeah, it has a lower mass than that limit, as far as we can tell. So when it
Okay.
gains material, it's not enough to push it over 1.4 solar masses. But because of that fresh supply of hydrogen,
It ignites fusion.
eventually, right? And so you get a flaring of the star, and you see a sudden brightening. Now, sometimes when these events happen, it's a one-time thing. But of course, that's very biased, because we've only been keeping records for several hundred years. So if a nova went off and you get that flaring, maybe it takes another 10,000 years to accumulate enough fuel from the nearby companion so it goes nova again. So ones that have been observed to repeat, so have gone off more than once, we call those recurrent novae. And this is one of these cases. This seems to go off roughly every 80 years. So if you could have really detailed examination, if you were close to the system and could watch, the transfer of material is such that after approximately 80 years, there's enough buildup of material on the surface of the white dwarf that it will ignite, and you get this nova event. And then it'll just die down over a period of weeks and months and back down to its brightness prior to when it went the nova.
And start the process over again.
And starts the process over again. So this occurs every 80 years. Now, the interesting thing about it is you might think, oh, does that mean I have to wait 80 years? The answer is no. That according to our calculation, this system, the star system, should go nova somewhere, the best guess, is around April, May of this year. Robert, we don't have to wait 20 years for this event. We just have to wait a couple months.
A few more months.
Now, there's an uncertainty in that, of course.
Of course.
Nothing happens exactly on time when you're talking about these type of things. So it could go off later on in the summer. You know, it could go off tonight, Robert.
Could.
So the thing is, if you have clear skies every night, you should go up. If you can see this constellation, and it's a summertime constellation, so it makes perfect that we can see it from where we are here. that you can go out and look at this constellation and look in that area that you see this red circle. Instead of seeing the one star, this is part of the crown, you'll see two stars. One of them, the new one, will be really bright, the nova itself. So look every night that you can.
So this will be low in the northeast right now.
Right now, yes, from our location.
From our location.
Of course, if you're in the southern hemisphere, if you're in Australia, and if you
might
are,
not be able to
and
see
if you
it.
are, good day, might. But if you're in Australia, you're not going to be able to see this event. This is always below your horizon. So this is a northern hemisphere constellation.
Cool. And I will also note that to see even the keystone, you're going to have to be in a fairly dark environment. So if you live in urban or suburban area, you're going to have to drive for a ways to get out away from the city lights to be able to see even the keystone, much less this nova.
So we have a question, how far away is this system? Beautiful question, because I was just going to mention it. As far as we can tell, this system is about 3,000 light years away.
Wow, okay.
That's the distance.
So that would explain then what one of my questions was going to be, which is, has nobody turned a good enough telescope on it to actually see that it's this accretion disk laying material down on the white dwarf?
Well, here's the other interesting thing. What do we have up there now that wasn't there 80 years ago?
Oh, wait a minute. James Webb.
Yeah, and that's sensitive to the infrared. So if you're looking at material, here's a good chance to study the system. And of course, if it's really bright, you kind of got to watch out for that, of course. But in the infrared, it's not going to be as bright as it would be in the optical, just because of the difference in the peak emission as it relates to the temperature of the surface of the star.
Should be interesting to see if somebody got some time to look at it with.
Yeah, and we also have, of course, interferometers, even out in the millimeter range, like ALMA and stuff, so you can do detailed observations with that.
If any of my friends at Chara are listening, maybe get a few hours of that time or something. I don't know.
Well, the good thing about it is for astronomers, this has been well publicized, which is nice to make people aware of it. It's to get to the non-astronomers to say, hey, take a look up in the sky in this region. If you see something new, report it. Right. Because that is the nova event, right? That's occurring. So we'll be on the lookout for that. So,
cool.
So we'll see what happens. So that's really interesting.
Yeah.
Now we're going to change the subject to something that's less exciting, if you like.
I don't know. It's pretty exciting.
Well, to some people, it can be devastating.
Okay, yes.
So if we want to go to the next slide, Robert, please. This involves the recent proposed NASA budget. And unfortunately, it's like this, right? We always want our own candy.
Right.
And I can eat a piece of candy, and let's say I only take a little nibble out of it each year, and it's designed to last 10 years before I consume it all. And I eat the candy every day, but I actually eat just a little less than what you thought. So instead of lasting 10 years, it actually lasts,
20,
30 years.
30, yeah.
At some point, you might say, well, that's enough of that candy. I'm tired of it. Can't I have something else? Well, that costs money to have something else.
Right.
Maybe we can't afford another candy for you. Eat the one you have. Now, what's going on here is that in NASA's budget, there are plans essentially to shut down the Chandra Xray Observatory. The Chandra Xray Observatory, you can see in the NASA image shown here, was launched from one of the space shuttles back in 1999. The Chandra Xray Observatory is the best X-ray space telescope that the United States has in operation today. In fact, it has been the best since 1999.
Right.
Now, an X-ray telescope, because X-ray photons coming from astronomical objects are blocked by the Earth's atmosphere. So, Robert, if I gave you money and said you had to build an X-ray telescope and it has to be in your backyard here in Grand Forks, it's not going to be very useful.
I'm going to hand you your money back.
Yeah.
Because it can't be done.
Yeah, it can't be done. You can't detect X-rays coming from beyond the Earth from ground-based X-ray telescopes. So you have to put these things in space. Mm-hmm. You got to get above the blocking effect of Earth's atmosphere. Now, this telescope there are a couple things we look at when we design telescopes. Number one is the resolution. Mm-hmm. Now, it turns out that the resolution, that is the ability to see detail. So if you think of something that looks really blurry, you're going to have poor resolution compared to something, the same object looks really detailed, really sharp. Maybe you're using a different instrument that has a much higher resolution. Now, the resolution of the Observatory is that it can detect the actual size of a dime if it's over 4.5 miles away. Its resolution is about a half an arc second.
And that makes me think of something, because people always go, well, if they can do that, why are bank cameras so blurry? And the answer is, you get what you pay for.
Yeah, just look at your Ring camera compared to something that you pay $5,000 for at a store or something, right?
Spend $500 million on a single bank camera, and you'll probably get pretty good resolution.
Yeah, it's best that your monitor can provide.
There you go.
So this telescope is the best in the world in terms of resolution. Now, there's a word there, if you look on the right side of the image, says on axis. And that's because if you look at sources that are not in the center of the field of view, essentially, they get blurry and blurrier.
Right.
So the best that Chandra can do is about a half an arc second when it's on axis. Now, there is, to be nice about it, there is a comparable, at least overlapping telescope that's also in space, launched by the European Space Agency. So anyone at European institutions have direct access to it. That's the XMM Newton X-ray Observatory.
Oh, so that's Newton.
But its resolution, the best it can do is about 5 arc seconds.
Oh, wow.
It can't reach the resolution that we have with Chandra. But its mirror is a little bigger, so it's more sensitive. Its light gathering ability, we say, is a little greater, so it can see fainter sources in the X-rays.
Right.
So the two of these telescopes are you can kind of work together, right? You can look at very faint objects, and then if you want high resolution, then as long as you can detect it in Chandra, then you can turn Chandra to look at that same object, to look at it in nitty-gritty detail. Now, these type of telescopes need to be operated, of course, right? You can't pay all the money to build a telescope, send it into space, and then say, okay, we're done with that mission, let's move on. No, it takes money to pay for salaries for people to upkeep the mission, to keep communicating, to process the data. I mean, if you win time on the telescope, you get to use the telescope, they send you back your data from space, and then they give you money to process the data. Maybe you have it to hire students, right? So you get students or grad students even, or even postdocs. In fact, as a disclaimer, here's another, this is the disclaimer podcast, right?
Yeah.
Another disclaimer, my first postdoc involved working on data from Chandra. So if it wasn't for the fact Chandra existed, I wouldn't have had that postdoc. It was at the Smithsonian Astrophysical Observatory at the Center for Astrophysics, and that's in Massachusetts and Cambridge. And so there are hundreds of scientists that work at this institution, and a lot of those scientists have a direct involvement with this telescope. So when this telescope goes away, a lot of jobs go away with it. And these are not just average jobs, these are very high-tech jobs, and a lot of them has to do with people that do work to the instruments remotely. If there's a problem, they troubleshoot it and get the instrument back up and working again, well as the people that process the data and so on.
They write new code to get the data down better, to analyze it better, pipelines as they're called. Yeah.
So this telescope is essentially, 24 to 20, almost 25 years old now.
Oh, wow.
And you think that's a lot of time, which it is, but it's still providing useful data. Now, how do you know it's providing useful data? Because every time there is an announcement, what happens every year in March, to request for new proposals, it's always oversubscribed by a large factor. In other words, it's difficult to get time on the telescope because so many other people are trying to get time on the telescope.
We laugh and say every now and then that we're going to start having an arena fight. Your proposal gets approved if you beat everybody else.
So if the telescope wasn't very useful anymore, in other words, why spend money on it, then why are people in great demand trying to use the telescope every year?
Right.
Now, to give you the idea of the proposed budget, there's some numbers that are there are in yellow font. And so for 2025, it's $41.1 million. And 2026, it drops to $26.5 million. That's a significant drop.
That's a significant drop.
Now, Chandra is already, almost optimized. They're at the point where you can't take away much more money out of the funding to keep it running before it's really useless, right? You may as well just shut the thing down. Notice that $26.6 million persists for 26 to 28, but then in 29, it's down to $5 million. What can you do with $5 million?
Pretty much nothing.
Close it up.
Close it up.
And you're pretty well there at that point in 2029. You're done with it anyways, right?
Right.
So you close it up. Okay, fine. You close it up. You shut down the telescope. What do you do with it? Well, it's not designed to come down. You have to, the deorbit part of things, I don't know how they're going to do that. You fall back on its own, I guess. That's the only way you can do it. Or unless you send something up to attach some kind of a thruster on board to controlled re-enter it and dump it into the Pacific Ocean or something. I think they're just going to let it come down, because either way it's expensive if you're going to try to do something controlled re-entry. But anyways, so you might say, okay, so now where's the next piece of candy?
Okay.
Well, there is no next piece of candy at the moment. But before we get there and talk about the future of X-ray astronomy, let's move on and look at some of the highlights from the Chandra X-ray Observatory. So some of the things that it has observed, and by the way, this data is available to everybody.
Yep.
If you're interested in looking at X-ray data taken from this telescope, they have a huge archive. So that data is accessible to everyone. You can log in on their website, download the data, learn how to process it, right? If you're interested in this sort of thing. It's not like it's hidden and the only people that get the data are the ones that submitted proposals and were awarded time. No, all that data becomes available to everybody in the world.
Right.
In some sense, it's a legacy type of system where that data will always be available for everyone forever, essentially. Now, some of the images that you see on this slide are some of the things that it looked at. It includes examining supernova 1987A, Robert.
Yes, indeed. That's the upper right hand.
And that's from, of course, the last podcast we did. We talked to Dr. Eden Sheldon about the discovery of that
Discovered
supernova.
this one, yeah.
And the Chandra X-ray Observatory is doing a lot of groundbreaking work and following what happens to the supernova remnant over time.
Mm-hmm.
And so we like, and of course, this is where the resolution really pays off. We want to look at all that nitty-gritty detail that you see in that upper right-hand corner, all those little knots that get lit up, they're energized by the impact of particles coming from the supernova itself. And of course, the thing in the very center that looks like a goldfish,
Yep.
the detailed study of the structure of that, because that ultimately can tell us about what's left behind and how these things change. And that's related to, you can think of hydrodynamics, it's related to astrophysics, it's related to explosions and then magnetic fields and how do they work and how does that affect things that you observe. All of these things are extremely important from strictly a physics point of view.
Indeed.
And you take away the eyes to observe some of this stuff, like Chandra X-ray Observatory, that's really going to have a major impact on the science that we're going to get from this closest supernova to hit in the last, 400 years? 400 years.
400,
yeah,
okay.
since the early 1600s.
Yeah.
But it's not just this thing. We looked at a whole slew of things, and these are some of the objects that you see here. They go anywhere from galaxy clusters to looking at interacting galaxies. In fact, the bottom left-hand corner that you see there. Yeah, and what's so special about that object, Robert?
Well, it's the most massive star that we can see, and it's going to go supernova and produce a nice light show for the southern hemisphere.
Would you like to observe an object that's ready to go supernova, studied and detailed, and maybe ever so lucky it actually blows up in your lifetime? This is one of those objects to look at.
It's, yeah. One of my colleagues, when I was in grad school, getting my degree in astronomy, this was his study. He showed that it was a binary star, actually. So
now, people have different, of course, opinions on this whole issue about what to do when, we're $34 trillion in the hole as a country. Don't ask me how you ever pay that back. I don't know. I don't even know what 34 trillion of anything is. And by the way, if you have 34 trillion pennies, please feel free to deposit that in my bank account. Thank you very much.
Right.
But it's such a large number, what does it really mean? I don't know. I'm not an economist, so I don't know the ramifications of having such a large
I do know
debt.
that with a nation that the debt doesn't correlate exactly to what debt means to us, but at the same time.
And the thing to really think about, though, is how much money we spend as a country per year.
Right.
And how does that compare to a few tens of millions of dollars?
It's a drop in the bucket.
Now, that's almost like, that's a rounding off error, right? This is probably money that's found all over the place by the different government agencies when you add everything together. Oh, yeah, we found $1 million that was laying over there. It was earmarked for something that never happened, and people forgot about it or something, right? It doesn't get included in the main annual budget or something, right?
Like you said, it's a rounding off error. That's how small it is.
So there's that issue, right? The amount of money to keep Chandra going is very, very tiny, less than a drop in a bucket
Right.
compared to what we spend every year as a country. But here's the other thing that bothers me. The other thing that bothers me is we went through all the trouble, all the effort, right, of sending up this telescope in space to do this fantastic work that people are dying to get time on, hence the oversubscription every year for proposals. It's still going strong. Why not support it until it dies its natural death?
See, that's what I say. Yeah. Why not?
It's almost like a car, right? I have one of my cars that we own, and it was built in 2007. And I don't know about you guys, but every once in a while I get the local dealership that I'm associated with call me up and say, there's a great demand for your car.
Yes, there is.
How would you like to trade it in and buy a new one? And my immediate response is, why should I buy a new one when this one works perfectly fine?
Right.
It gets me from position A to position B. That's all I ask. And the car has long been paid for. Why should I go and get a bank loan to afford a brand new car? Which nowadays, if you haven't looked at the prices recently, is pretty expensive.
Pretty expensive, yeah.
So why should I do that? I don't need to do that. So why should I go and take money and get rid of the Chandra Xray Observatory when it's working fine? That's the point.
Right. Especially when keeping it working is, as we've commented, a rounding off error.
Yeah, it's a minimal amount of money.
It's a huge amount to us, but we're not a government.
Now, if you feel strong enough on this issue that you would like to do something about it, then go to this website. And it's up to you. Like, disclaimer, this is my own personal opinion. It's nothing to do with the University of North Dakota or anybody else affiliated with it. I've gone here to this site myself and entered my name in this petition. And so if you want to save Chandra, when do government officials listen is when people raise a stink.
And
right?
During election years.
Yeah, well, the squeaky wheel gets the grease. That saying
Right.
is there, not, there's something to that saying, obviously. Yeah. So if you want to say something about this, if you're not in favor of the canceling of the X-ray observatory, let it die its natural death. Let it get to the point where maybe problems build up where it's no longer useful, then we'll get rid of it.
Right.
Okay? Now, if there was another telescope available, another X-ray telescope that we can turn to, okay, well, I'm all for that.
Now let it die.
And then let it die, and let's move on with the new generation of X-ray observatory that will be hopefully better and stronger than the last one. In fact, there have been plans with this. When I was at the Smithsonian Astrophysical Observatory way back in 2002, so I was there from 2002 to 2005 for my first postdoc, there was talk even back then of what are we going to do after Chandra dies? And what's the next great X-ray observatory that we could put up? And so there have been many plans, but nobody has agreed to do this, to spend the money that now they've been cutting metal, ready to send this thing up. So the latest, greatest proposal is this Lynx X-ray Observatory. And there's some comparison that you see there, especially on the right-hand side. When is it going to be launched? Well, as far as I know, it's not even been built yet, not even started to be built yet.
Probably not even on the designing the hardware stage.
A lot of times these spacecraft, when you start to design and build them, it usually takes about 10 years for the building process to be completed. Oh, I'll have this built in 5 years. Don't worry. When 5 years goes by, we need another year. Oh, when 1 year goes by, we need another. And then it ends up being 10 years anyways, no matter what you promise at the beginning. And so this thing then, this telescope, the next generation, may be launched in 2036. Maybe. There's a question mark there. So what do you do if you shut the telescope essentially down now? What do you do for what happens in the next roughly 10 years that you're waiting for this telescope to go up? The next one, the Lynx mission. In fact, it could be 15 or 20 years before it actually goes up. What do you do with all those people, right? Those people who have been trained in this high-tech technology, this high-tech business. What do you do with those people? They get laid off and they go elsewhere. So in that sense, when you're ready to do things with this mission, all of your expertise has bled away. Maybe they went to Europe, which is designing their own next generation X-ray observatory.
Or they've retired by
Or they retired, or they went into something else, never to return.
Right.
So you train people over couple decades of how to do the work properly, right? These are the best people in the world that are operating the Chandra X-ray Observatory when it comes to the instrumentation and the analysis of the science. And now you're essentially throwing them out and say, thank you for your service. See you later. By the way, we'll hire your grandson when we get the next one out.
Yeah. Of course, your grandson now won't know what to do with any of this stuff because it's back to being brand new.
Exactly. Now, do we need a next generation of X-ray observatory? Yeah, we need a next generation, but let's not kill the present one that's still working.
Until it's working.
Maybe there'll be an overlap. Maybe when the next one's ready to go up, this one will be finished and it'll just die on its own and that'll be the end of it.
Right.
Of course, if it dies tomorrow just because of instrument failure, so be it. Then yes, you have to do that. You take the money and spend it on this project instead, the Lynx X-ray Observatory.
Right.
But I wanted to just mention a little bit of the comparison. So first of all, the plan anyways is to send this to the Lagrangian 2 position.
L2, yeah.
So you know what's at L2 now that was put up there a couple of years back?
Isn't that the Parker Solar Probe?
No.
No, that was the Sun Diver. SDO? No, I don't know.
James Webb Space
Oh,
Telescope.
it's at L2?
Yeah.
I thought it was at L4.
No,
Oh.
it's at the L2 position.
Okay.
And so it will go to that position. And the other thing, notice, is its collecting area, 2 square meters. Now, compare that
Wow.
to Chandra, 0.04 square meters. Now, the area of your detector, like the area of, if you think of a reflecting telescope, the area of the mirror. If you think of a refracting telescope, it's the area of the lens. If you think of an X-ray telescope, it's the effective area of the collecting surfaces. Now, this telescope will have a much larger area, collecting area, which means it can see a lot fainter in a given period of time
Right.
than the Chandra X-ray Observatory. So it is going to be way more sensitive in the X-rays. So it can see things that otherwise are invisible to Chandra. The other thing that's nice is in terms of the resolution, it's going to have the same resolution as the best that Chandra delivers, the 0.5 arc seconds. But instead of, in Chandra's case, where that highest resolution is near the on-axis position, the optical axis part, right, the middle of the collecting surface, it's going to be spread over the whole field of view.
That will be nice.
Of the X-ray Observatory. So it would be 0.5 arc seconds all over the imaging area that the detector can gather. So over the whole field of view. That's what the FOV means there, field of view. So that's going to be really nice.
That would be nice.
And so that's going to allow us to do really detailed surveys a lot better than you can with Chandra. And so the telescope, yeah, it's the next generation. It's going to be better. Why would you put up something just as much or the same capability or less? You're not going to, right? If you're going to spend money,
just leave the other
leave
one
what you
up.
have up there. If you're going to spend money, you want to make improvements. But
Right.
the point is, this thing is not going to be ready to at least 2036. Chances are it'll be 2040 by the time it gets launched.
Yep.
2040. What are you going to be doing in 2040, Robert?
Let's see, that's
Correcting labs.
no.
UND?
Well, probably because I will be able to retire Sunday 3 hours after I died.
Right.
So
In other words, it's a long ways to wait,
Yes.
for the next generation to go up there. And remember, this stuff can't be done from the ground. This observations in the X-ray, it has to be done through space.
Yep.
Now, I don't know what else you can do except go after the government and see if they will throw a few peanuts our way and keep the thing running until it dies on its own. I don't know what to say, but
Right.
that's the status of the budget as it is right now, unfortunately.
unfortunately,
Now, Robert,
yes.
this is the time when we talk about somebody that we've talked about in the past from the University of
Of
Ottawa.
Ottawa, yes.
Gupta has put out another paper. This time it's been published in the Astrophysical Journal, APJ.
How was this stuff getting through?
Well, we'll talk about that in a second, but here's the paper. So it was published 15th of this month. The title is Testing CCC plus TL. And of course you say, well, what the heck is that? We're going to look at that in a second. Cosmology with observed baryon acoustic oscillation features. So what is the CCC? Well, we put up a copy of the abstract. It's covariant coupling constants, and the TL is tired light. Yes, it's the tired light idea that was first popularized by Fritz Zwicky back like in 1929, and it came shortly thereafter the evidence that Hubble amassed together and published of the expansion of the universe. That there's this relationship between the redshift of a source of light and a distance to that source.
Right.
So the relationship is that the further away a galaxy is, this is how it's used in astronomy and cosmology, the further away a galaxy is, the greater its redshift. And that's due to the expansion of the universe. So if there's more space between galaxy A and galaxy B is going to be traveling faster away from galaxy A than if you compare, let's say, galaxy A and galaxy C, where galaxy C is much closer. There's less space. Every length of space is expanding at a certain rate. So if there's more space between you and some distant object, it's going to be traveling faster away from you. The upshot in all this is the simplest explanation of all of that is that the universe is in a state of expansion. Right. So this was known or published since the late 1920s, and most people accept that.
Right.
Now, Fred Zwicky came out in 1929 and said, well, what happens if the light coming from these distant objects interacts with material on the way here? It would lose energy. And if you lose energy, what happens as the photons do not slow down and travel slower than the speed of light, what happens is that the wavelength of light stretches or enlarges, and you have a redshift effect.
You have a shift to the redder colors.
But there is other effects that should be noticeable in that, and one of them in particular that we talked about several podcasts ago involves the leftover heat from the Big Bang. This is the cosmic microwave background. There are features in that cosmic microwave background that we observe today, and those features will be affected if tired light is correct.
Right.
Over cosmological scales.
They would be smeared out, wouldn't they?
Yes, so these features involve, for example, the passage, if you like, of that thermal radiation from the very dense and hot phase in the early history of our universe, and the effect that material has on those photons. And some of those effects are well modeled. For example, there's something that we call the Senyev-Zadovich effect, named after Senyev and Zadovich. And what it is basically when photons travel through the hot intercluster medium of clusters on their way here, they interact with those electrons. They get inverse Compton scattered. So if you know a little bit of physics, you'll know what I just said there. In other words, they're affected by these hot electrons, and that the cosmic microwave background is affected by that. Mm-hmm. You see a non-uniform sort of measurement of these photons coming from that particular little spot on the sky. Well, that's well mapped out. That's well understood.
Right.
The other thing that we have are these baryonic acoustic oscillations. So if you want to go to the next slide, Robert, We'll try to explain what this is all about. So on the panel on the left, very early on in the early history of the universe was so hot that basically the baryons and the photons are coupled, as we say. They interact with each other. Just like we have interaction with light with electrons. You know, that's then you think of a fancy phrase that would explain that interaction today in modern form would be a quantum electrodynamics. In fact, Richard Feynman won the Nobel Prize as part of the explanation of QED. And there's a nice little book that Richard Feynman wrote for the layperson. It's called Quantum Electrodynamics. If you look that up on Amazon or your favorite supplier of textbooks, there's a nice layperson's book called QED by Richard Feynman. It is not very long, but it's written from the point of view that the average person with just a little interest in science could actually understand. And one of the main tenets in that book, and I have a copy myself, bought many years ago when I was just starting, I think, university at the time, was that photons love to interact with electrons.
Yep.
Okay? So when you have photons then in a location where there's lots of electrons, because it's so hot, normal atoms don't exist. They're completely, whatever atoms are around, they're completely ionized because of the high temperature. Then photons and electrons then interact with each other. And what you have are these overdense and underdense regions throughout the universe. We know that's the case. Why? Because we can look at the temperature of the leftover heat from the Big Bang and observe it at multiple locations across the sky. And note that it's not the exact same temperature everywhere. There are what we call temperature anisotropies, is the technical term. That means one little patch of the sky can have a slightly different temperature than some other random patch on the sky. The temperature differences, the fluctuations in the temperatures, are on the order of about 1 part in 100,000. So they're almost exactly the same, but not quite. If they had exactly the same temperature, that means that the density of matter was exactly the same everywhere. And there's no overdense regions and no underdense regions.
In other words, there would be no galaxies, no stars, no nothing if it was all smooth in the same temperature.
We need those overdense regions to build up their mass, ultimately turn into things as Robert mentioned. So we need to know where ultimately the structure of the universe comes from, and it's from these overdense regions. And indeed they exist. This was discovered back like in early 1990s by the COBE mission, the Cosmic Background Explorer mission, that gave the first detailed look in space of the leftover heat from the Big Bang, which was discovered and first measured in 1964, and then I think the paper came out in 65 of the implications of what those measurements. That's where Penzias and Wilson won the Nobel Prize in Physics for that discovery eventually.
Yep.
So early on in very early history of the universe, then, you have these overdense regions where photons and electrons are coupled. They are connected to each other, and they create a pressure that pushes outwards. But in these overdense regions, of course, you have also gravity, and gravity is trying to collapse these overdense regions. So you have both an internal pressure from the coupling of the photons with the baryons, as we say, with the electrons mainly, pushing outwards, and gravity trying to squeeze inwards. And this whole thing is in a state of fluctuation because of the rapidly expanding universe at a very early time in the history of the universe. And what you have essentially is a sloshing back and forth of material. That generates sound waves. This is the acoustic part of the baryonic acoustic oscillations.
So in space, someone can hear you scream.
In this part, in this
the universe scream.
Well, you know, if you were inside a dense enough cloud of interstellar matter, sound can travel through that cloud.
Right.
So the answer is yes. If it's dense enough. If you were in the vacuum of space, the answer is clearly no.
No. The universe can still be heard screaming, but you wouldn't.
Exactly.
It's not dense enough for your small vocal cords.
To oscillate material that ultimately that oscillation would impact my eardrum.
Right.
And I would denote that as sound, right? Detect it as sound. But in this case, you have these basically sound waves that are generated, and because of the rapidly expanding universe, this thing freezes out eventually as the temperature drops. And it's like you have standing waves. If you know a little bit of physics, what a standing wave is, you can vibrate a string to the point where you vibrate it fast enough, you get this beautiful stationary-like structure. You can see the different wavelengths in the string that you're vibrating. And if you change that frequency, it looks like a jumbled mess until you reach the next mode of vibration, a standing wave sort of thing. So anyways, what happens in this case is that its structure piles up on the edges of these standing waves, essentially, what we call the sound horizon. I'm trying not to be too technical so people can follow along here. So in other words, there are preferred sort of angular scales at which you find material. And that is where you would build up galaxies. That's the idea. Now, the actual data was actually taken by the Sloan Digital Sky Survey. That's the plot that you see on the far right. Eisenstein, I think is his name, is the person et al. That I should have had the credit here. The first paper that published the result of this. And what you have plotted on the vertical axis is a correlation measurement. So in other words, if I look at some random location in space, if I go off by 1 degree in some other random direction and say, what's the chance of finding another object there, like a galaxy?
Okay.
That's a measurement of the correlation function, the 2-point correlation function, as we would say. That's what's plotted on the vertical scale. And what's on the horizontal scale is just the separation between things. Now, it has the expansion of the universe folded in there, and when you do that, we call it co-moving separation. So in other words, if something is separated by a certain length scale, it will remain separated by that length scale regardless if the universe expands, because we're taking that expansion into consideration.
Okay.
That's the co-moving scale.
Co-moving part. Yeah.
Right. So in this, you're seeing the correlation function, and notice when things are close together, so that would be on the bottom left on that plot, then notice that the data is way up high, so there is high correlation. But as you go to greater and greater separation, as you move to the right, according to the horizontal scale, notice the data points drop and drop and drop. It becomes less likely to find other structure. Okay? And then as you go along, all of a sudden you get this little bump at around 100. Okay, that's 100 megaparsecs. So that's another length scale. 1 parsec is 3.26 light years. and a megaparsec is then 3.26 million light years, and this is 100 times that. You get this little bump. And what you're actually measuring is this sound horizon position, where the material piled up on the edge of these bubble-like structures, because that's the farthest that the sound waves could have moved at the time that they were created in the early, rapidly expanding universe. We should see an excess measurement or correlation at that position. And you can actually use that as a ruler, that is, as a yardstick, when we can see the co-moving separation. That tells us a lot about what was the size of the universe at that point in time when this structure, when the photons decoupled with the baryons.
Right, when they were able to just blow through and move freely about.
Now, this actually has an impact on the leftover heat from the Big Bang, and this impact can be seen if we measure what's called the power spectrum of the CMB. We should do a whole new podcast on that.
Power spectra. Yeah.
But what I'm trying to say here essentially is there's a lot of evidence that does not support that paper by Gupta. If you want to go to the last slide today.
Okay.
The ramification of this new paper is that there is no dark matter. And that's the thing I want to finish up today addressing. No dark matter. Now, we have lots of evidence for dark matter. We have flat rotation curves. That is, the galaxies and the stars in the outskirts of galaxies are traveling too fast than what they should be. If there was no dark matter, we'll also go into this in a future podcast. But the one thing I want to show you here is what we call the bullet cluster. This is a combination of image taken with Chandra Xray Observatory.
Okay.
That's the pink light. The blue light then is where most of the mass is located according to gravitational lensing. And what you're seeing here is actually two galaxy clusters that went through each other and are now passing by. So the one cluster that you see in the blue sort of haze around it on the left side, that was actually on the right side. And there's a concentration of galaxies on the right side in the blue haze. That was actually on the left side. So they pass through each other. Each of those clusters contain hot gas. And when those clusters went through each other, that hot gas filled up a large fraction of the volume of space that they occupy. That interacted with each other, creating these shock fronts that you see in the pink. That's the X-ray data. And one of the shock fronts almost looks like a bullet passing to the right.
Hence the name of the cluster.
Hence the name that's given to this system. And so the gas, which is made up of ordinary matter, protons, electrons, and so on, that gas couldn't pass through each other. But the dark matter went through each other because it's non-interacting. It doesn't interact in the same way like through electromagnetic forces as the normal matter that's there, the baryons, the one that's emitting the X-ray light that you can see as the pink light in this image. So in other words, not to get too technical here, we would not have the bullet cluster like you see here if it wasn't for the presence of dark matter. If there's no dark matter in the universe, please explain the bullet cluster.
And he can't.
And you can't. So there's a lot of things that we can get into to describe, this paper and what it really means, its implications. But the thing is, Robert, I'm always in favor of publishing these things as long as it doesn't outright violate known laws of physics.
Okay.
If it's one of these things where, well, we don't quite know, let's publish it, maybe that'll spark experimentalists to go check in detail at the tired light hypothesis and all these kind of things. I'm all in favor for that. That's how science advances. But if the paper violates locally the conservation of energy, it violates the second law of thermodynamics, entropy and all these things, don't publish it, shut it down immediately.
Okay.
Because then it's clearly wrong.
You're a little more generous than I am. I'm like, if there's evidence to say this is nonsense, it's
Robert,
nonsense.
We never went to the moon. How do you argue that we did? You take everybody there and show them the footprints on the surface, you see?
Okay.
So in this case, how do you get rid of people keep bringing up tired light all the time? Let's measure it with modern technology. Let's measure it precisely enough today that we can dismiss this idea forever. That's my view on it.
Okay, that I'll agree with. If somebody wants to bring it up, okay, let's just shut this down.
But if you're interested in science, if you want to get involved and looking at different hypotheses and seeing if they're right or wrong, all of these kind of nice things, please come to places like the University of North Dakota.
Absolutely.
We have a lot of programs here, both on campus and online. So if you're interested, if you're like a high school student trying to figure out where you want to go in the fall or maybe the fall after that, please consider coming here to UND. We'd greatly appreciate it. And I'll guarantee one thing, if you come to UND, you're going to learn a heck of a lot more than when you leave than when you first arrived.
Absolutely.
Guaranteed.
So,
now, our next podcast will be on Tuesday, April the 2nd, and we're going to have a very special guest with us, somebody local.
and somebody we've had on before.
Yeah, and that's Dean Smith. And we're going to talk about the eclipse that's coming up on April the 8th, for those of you lucky enough to be able to see the eclipse, and the weather cooperates.
And the weather cooperates.
Fingers crossed. So he'll talk about that eclipse as well as other things that you can see in the sky, and now the spring.
Right? Spring has sprung.
Spring has sprung.
Supposedly.
Now, I always leave you with a quote. Mm-hmm. And today I decided to get a quote from Alan Turing. You remember Alan Turing? He's famous for cracking the Enigma.
The Enigma code.
From
one
World
of
War
the
II,
original mathematician computer programmers.
The famous movie, The Imitation Game, starring Benedict Cumberbatch. You remember him from Star Trek. So he played Alan Turing in the movie. I actually watched the movie. It was actually a pretty good movie. Anyone who are into that kind of stuff would really enjoy it. And so the quote of the day is a quote from Alan Turing, and he said, "Science is a differential equation. Religion is a boundary condition." Thank you very much for watching.
Have a great day, folks.